Anybody have any questions, concerns? If I remember correctly, our first available date for the 5-minute presentations is next Friday after the exam's over. So I haven't checked to see if anybody's signed up for that, but if so, let me know if you have any questions. Yeah. Wednesday. Yeah, the first 5-minute presentation is Friday, which is after Wednesday's exam is over. I also, just about time to start now, yeah. I posted just minutes ago on the website 2 things that are related, excuse me, to reviewing for the exam. One is an old exam from this point in Physics 110 that I've given before. A second one is a collection. It's not an exam, although there are some old exam problems mixed in it. It's just kind of a grab bag of lots of problems. And also I've posted the solutions to both of those. Now, of course, I don't recommend that you use them by having the problems next to you the first time you're going through them, and then the solutions right next to them and going, oh, yeah, I know how to do that. And of course, everything looks easy when you watch someone else do it, or if you see a solution laid out. So you want to really get the idea of whether you're prepared for the exam by sort of going through once and then hitting the point. You could look at the answers and say, oh, I didn't get it right. Okay, let me go look at the detailed solution on that one. And you're welcome to, of course, ask me about that in class on Monday. It's looking like we might get very close to the edge of the end of chapter 4 today. And I've got the chapter 4 homework due Monday night, I believe. So my goal probably for Monday is just to have time to practice, maybe bring a little more practice stuff to class, but my first priority is any questions you guys have. So if you want it to be just a Q&A kind of problem solving thing at the board, that's fine with me. I think it's a good time to kind of not keep pressing forward with material that's not covered on the exam just because of where we're at right now. So look for those. Also, the thing we did in lab this week, those kinematics practice problems, those are very good practice for the exam too. Lots of the 2-dimensional kinematics. You'll see more of those on the stuff I posted. And that is also posted on my website too. So look for center column, first 3 rows are the stuff kind of relevant for exams. And I've mentioned to several people, anytime you have an exam with a professor, take anything that they have written as your first line of defense for what's most important or most likely to appear on the exam, right? The homework problems, some of them are great, some of them are too hard, some of them are too easy. They're all written by people who are not me, so I probably wouldn't phrase it exactly the same way. But if you see an old exam by me, that means that I'm saying that's at the appropriate level for an exam. So it really gives you an idea of the kind of thing to expect. And do think about the types of big problems that we've done so far. We're still going through some of them in chapter 4, which is important too. But chapter 3, of course, that ballistic motion kind of problem is very big. And since we spent so much time on it, the position, velocity, acceleration graphs for 1-dimensional motion, those are something that you'll see on the old exam. So take that as a strong hint. You're almost guaranteed that one of those is going to appear on there, and a ballistic motion kind of thing, and a 1-dimensional motion, and some force kind of things that we're working our way through now. So try that homework over the weekend. If you haven't gotten into it, try to finish it before Monday, and then we can answer questions during Monday's class or in office hours. All right, where were we? We were trying to answer a question that involves some strings, and I think I had just mentioned the properties of strings that we're going to assume in Physics 110. They're not necessarily universally true, but we're going to assume our string is light, like it's fishing line or just something made of like thin cotton or something like that. So compared to the things it's attached to, it has almost no mass. And so we're going to neglect its mass. There's something called a tension. We're going to assume the tension is uniform through the length of the unbroken piece of string. And the meaning of the tension practically is that whatever the tension is, it pulls on the objects it's attached to at its 2 ends along the direction of the string towards the center of the string with that force. So a tension is a force, has SI units of newtons, okay? And all that I'll sort of abbreviate by light string. If you have a piece of light string, you can count on that. But in the homework, if you see a cable, a cord, a string, a wire, all of those mean the same thing. And we had just started looking at this problem. This was the motivation for it. Here I've got two objects connected by a string, and then they're being pulled by another string, which someone is pulling with a constant 5 Newton force being applied to the end of it. And I think what we talked about at the end of last time was which block has the larger acceleration. And what was the answer to that? They have the same acceleration because they may as well be glued together. They're kind of moving as a unit. At every instant, they have the same velocity. And so if their velocity as a function of time is the same, they have the same acceleration. And so both are the same. The second question of A is, what is the acceleration of block B? And well, that's the same as the acceleration of block A. So I could calculate the acceleration of either one. And in fact, to do that, we're going to do something a little bit different. Rather than focusing on block A or block B and doing a free body diagram, since these things are kind of moving as a unit, they may as well be attached by a rigid rod, and I could think of them as a 3 kilogram object all together. You know, if they were moving around in a floppy way and moving together and apart, that wouldn't make as much sense. But here, because they're moving as a rigid unit, the string is not stretching. I should also say, you know, in my string thing, I don't mention this, but we assume that this string is not stretchable at all. It is completely rigid. So when you pull on it, it never, like, it's not stretchy string like elastic. So these are moving as a rigid unit. So let's calculate the acceleration of both of them together as a unit. So my free body diagram is going to be a single 3 kilogram object. Let me go to the board and just work it out. Let's calculate its acceleration. I've got to think about all the forces that are reaching in from the outside in my video here. I've got a 3 kilogram object. Notice no artistry there. I'm just putting a blob with a 3 on it. I'm going to take this direction to be up from the surface of the Earth. And what forces are reaching in from the outside and pulling on that object? Well, there are some reaching in from the outside. I don't have my picture up anymore, but yes. Yeah, so this 3 really is a substitute for a 1 connected to a 2 or something like that. One of the forces is a string pulling on it like this. And so someone was pulling with a 5 Newton force on one end. That means the string is pulling with a 5 Newton force on that person's fingers. That's Newton's third law, right? If I'm pulling on it with 5 Newtons, it's pulling on me with 5 Newtons. And that means the tension in the string is 5 Newtons. And that means it's pulling in the direction of the string on the edge of this 3 kilogram object. So that's a little bit of thinking required there, but there's a 5 Newton force being exerted to the right in the picture. If we think of this, which way was it? Is the 2 on the left? Yeah. So let me draw a cartoon here, just so I remember. 2 connected to 1, connected to this string with a 5 Newton force in it, and they're sliding on a frictionless surface there. And I'm just gonna, in my mind, I'm thinking of this is my object. Okay, and I'm looking for forces that are reaching in from the outside and pulling on that object from the outside. I'm not going to consider, of course, there's a tension in the string and it's pulling on part of it and it's also pulling on part of it over there, but I'm not going to concern myself with it any more than if I'm thinking of my object as this block. I never include the force of the left half on the right half and the force of the right half on the left half, right? I mean, we're only looking for forces from the outside. There is a force of the left half on the right half if I start pulling it along, but that's not something that's coming into it, right? So since that string is internal to my object, the subject of my free body diagram, that force doesn't come in. We're looking for things outside pulling or pushing on it, right? What else is pulling or pushing on it as it's moving? Gravity, certainly. Has a mass of 3 kilograms, so our formula is mg. So here's a vector of length 3 times 9.8 mg going down. What else is pulling or pushing on it? The plane, right? And we're told it's a frictionless plane, and we already talked about that means that it has to put a force on the object that's sliding on it in the direction perpendicular to the surface. I'll label it like Giancali does, I think, Fn, normal force. Any other forces on it? I can't think of any reaching in from the outside. There's no friction force here because it's a frictionless plane. All right, so that's step 1. Step 2 is put some axes. Everything's horizontal and vertical here, so there's not a whole lot of thinking we have to do. I'm going to take x horizontal, the direction it's going to start moving, and y vertical. And honestly, I'm not going to concern myself with y at all in this. Let's just go right into the sum of the force x components equals max. That's x components of Newton's second law. Okay, what's the x component of the normal force? 0. Weight force, 0. So the only force I need here is 5 newtons. That's the only of the 3 forces that has a non-zero x component. And it's all along x, so it's all 5 newtons. Going from the tail to the tip, I move by 5 newtons distance along the x direction. The mass, this is always the mass of the object in the free body diagram. So this is a 3 kilogram mass. And then AX is what I want to solve for. So that's easy. It's 5/3 in SI units. And that is meters per second squared. So 5/3, 1.67 approximately is a decimal. All right, so that's the acceleration of the whole mess. That means it's the acceleration of block B and the acceleration of block A, however you want to ask it. Sometimes I ask things in ridiculous ways just to see that you get that it's not so hard. Okay, let's do a few more of them. I'm going to leave you to finish up the last few. What's the tension in string 1? String 1 is this string right here. 5 newtons. No calculation to be done there, right? If I'm pulling on it with 5 newtons, it's pulling on me with 5 newtons. That's Newton's third law. And by definition, that's what the tension means. It's how hard it's pulling on the things on the end. What's the x component of the force string 1 applies to box A? How would I figure this out? I don't have that now. So we're saying, wait, maybe we do. Box A is the one on the right. Okay, yes. This one, there's no calculation to be done. What is the x component of the force? And I guess I didn't really need to put this on there. In the picture, isn't it true that there's an x-axis already drawn? So we don't really have a choice here. What's the x component of the force that this string is exerting on this box? Is it positive or negative? It's positive. It's pulling it to the right, and that's the positive x direction. And what's the magnitude of the force? 5 newtons. So this is just checking that you understand the definition of what tension means and how tension is related to the things on there. So the answers to both C and D are 5 newtons. Now, let's just say one word about E, and then I'm going to leave you with E, F, and G to try for a second. What's the tension in string 2? Okay, that's the one we've been ignoring here on my analysis here. This free body diagram is not going to help me because its force didn't come into that at all. But we want to know the tension in string 2, or equivalently, the force it's pulling to the left on the 1 kilogram, or the force to the right on the 2 kilogram. Those are all the same thing. If I want to use a free body diagram, what object should I use? Look, maybe if it's string 2, maybe I'll call this T2. We want to find out what T2 is. The 3 isn't going to work as a free body diagram, so I can choose the 2 or the 1. Can anybody think of any reason why either one of them might be slightly simpler than the other? Turns out they'll both work. I have only the slightest preference for one of them. if I do F net x equals max, how many forces are going to be pulling along the x direction on 1? 2, right? It's got a string pulling to the right and it's got a string pulling to the left. How many are pulling on the 2 kilogram? Just 1. There's just 1 string pulling to the right. You could try it the other way. You'll get the same number, but let's try the 2 kilogram as the subject of our free body diagram. Here are the forces. I'm not going to use the normal force and the weight force, but they're in the free body diagram nonetheless, right? And I've got the unknown T2. Whatever T2 is, that's exerting a force to the right on the 2 kilogram mass. And let's do the sum of the force again. We're given the plus x direction, so we don't have to choose our axis. Sum of the force x components equals max. And well, I'll let you finish it out. Why don't you finish that, figure out what T2 is, and then also do the next 2 parts, which again, there's not really a calculation to be done in F and G. Okay, the answer for that one, E, is 3.33 newtons. And there's only like half a step to get to the next 2 parts. So let's work that out here. This has 0x component, 0x component. You gotta always pay attention to what component are we doing. Don't mix x and y components. You're either doing x F net equals ma or y by itself, but never mix them in the same equation. 0x component, and this one's x component just comes in with a plus sign, and I don't know what to, so we're just going to call it T2. That's our variable. The mass is always the mass in the free body diagram, so that's 2 in SI units. And what's AX here? Yeah, it's the same thing we found. We're talking about the same situation, and we said all of these things are moving at the same acceleration, so 1.66 meters per second squared. Okay, so that's 3.33 newtons is T2. Again, I'm just thinking, put in all SI units. So this is a tension, it should be in newtons, right? So in SI units, I just put the newtons on there without thinking about it too much. Questions on that one?
Yeah. Just to double check, the acceleration you used is the same one we solved for in the problem that's to the left of it, right?
Yes.
Okay.
And that's because in the problem to the left, we were thinking of finding the acceleration of everything moving as a unit, but that's the same rate of acceleration of this block or this block. They're all moving as a unit, so they have the same acceleration.
Right. Yeah.
Good question. Okay, F, what's the x component of the force string 2 applies to box B? You got to look at the diagram. So box B is this one, and this is string 2. String 2 is pulling on that 2 kilogram direction, so it's going to be a positive x component, and the magnitude of it is whatever the tension in the string is. So it's going to be plus 3.33 newtons is the answer to F. G, what's the x component of the force string 2 applies to box A? This is box A. You look at the diagram printed out. T2 is pulling on it in that direction with its tension. Its tension is 3.33 newtons. So that's a negative X component. So the answer to G is minus 3.33 newtons. You always got to pay attention to which axis you chose, or in this case, we were given the axis. Any questions on that problem? Good. Let me show you something that might feel a lot different, but it's actually almost identical is a problem. Here's a 2 kilogram block butted up against a 1 kilogram block, and they're sliding again on a frictionless horizontal plane. And instead of pulling from the right on a string with 5 newtons, I'm pushing with a 5 Newton force with my finger over here, and it's going to accelerate as time goes on. Suppose I want to find, this is printed in your thing, right? I think this is problem 3 in here, yes. So the questions are, what's the acceleration of block B? Now, given what we just did over there, how might, let's see, B is this one. This is A. What's the acceleration of block B? Anybody have an idea how I might solve that? Given what worked over there? Yeah. Yeah, I'm going to draw a free body diagram for this whole thing because they're moving as a unit. So everything's acceleration is the same, right? They're all, the 1 is, the 2 is, or the 3 together, they're all accelerating to the right at the same rate. So I would make a free body diagram. Of course, there's a normal force upward on these blocks. Of course, there's a gravitational force. What I'm concerned with is the horizontal forces. No forces from this side, from the outside, but there is one from this side, 5 newtons. You might be tempted to draw it that way, but again, we usually conventionally draw the tails attached to it. So even though it looks like it's pulling and I'm pushing there, no difference in Newton's law, right? We're only concerned about components and what it's being applied to. So the answer is going to be the same. The acceleration is 1.67 meters per second squared. Look, it's the exact same problem over there, right? F net x equals max is exactly the same. B asks, what's the x component of the contact force block A applies to block B? A and B are butted up against each other, and we're asked, how hard is block A pushing on block B? Well, let's see. B is pushing on A in that direction, right? So A is pushing on B in that direction. That's what we're asked for. That's a negative x force component. We're using the same axis there. So I might write that as FA on B is, let me put in a minus sign. I know it's negative, and now we're just going to figure out how big it is. And I could do that by, again, it's not going to come into this one because it's an internal force in the middle of the 3. So I can use either the 1 or the 2. Let's do a free body diagram for the 1. What forces does it have on it? Well, there's nothing pushing horizontally from this side. Of course, it's got a normal force and a weight force. There's nothing pushing on the 1 from this side, but from this side, the 2 is pushing on it. So I might label this as F2 on 1. Just to remind me what it means there. Okay, and so when I do the sum of the force x components equals max plus x again going in that direction, the F2 on 1 comes in with a plus sign because it's pointing in the plus x direction. And that's going to be equal to the mass in the free body diagram, 1, times the acceleration that we found, and the acceleration was exactly the same as the one from the previous problem. So it looks like F2 on 1 is 1.67 newtons, right? That number is going to be in newtons. We were asked for F1 on 2 or FA on B. So that one's going to be negative 1.67 newtons because it's 1 is pushing on 2 in that direction. Okay, almost the same problem. So when things are butted up against each other or attached by strings, the method is really the same. It's just in this case, I write it as a contact force instead of a tension.
Dr. Kelly?
Yes.
Why do you use the mass of block A instead of block B?
Because I could have used block B, just like over here. I could have done the free body diagram for the 1 and gotten it out of there. Had I used the 2 kilogram block here, it makes it slightly more complicated because the 2 kilogram block has a 5 Newton force going to the right on it, and it's got F1 on 2 going to the left, and that's what I want to find out, right? And of course, it's got a normal force and a weight force that balance each other out. So I would do sum of the force x components. 2 forces come into it, but when I solve, I should get exactly the same number. The only reason I chose the 1 is because the 1 only has 1 force on it, and it was very directly related to what I was asked about. Just 1 Newton's third law reversal to get it. Is that enough, Nafis?
Yeah, so then like the force of block A on B would be, would it be like -1 times 1.67 or?
No, whenever we draw free body diagrams like this, notice I never put any minus signs on these numbers. This number, and this symbol here represent the length of these arrows. So when I write down Newton's second law and I solve for F1 on 2, that's telling me how big or the magnitude of F1 on 2. And then if I want an x component, I'm going to have to put in a plus sign or a minus sign when I consider which way I know it's going relative to the axes that were chosen. So you'll find out that F1 on 2 comes out positive here. And then I say, oh, we were asked for an x component, and this has a negative x component. So I'm going to put an extra minus sign in the answer.
Okay. Yeah, I think I was getting the third law confused with like the second law.
Okay. All right, let's go back to slides and see what's next. And I think, so let's see. If we forward through all this stuff, this is what we were just doing here. So no need to talk about that. Here's our next problem. I'm sure you read about this in the reading. This is something called an Atwood machine. And again, I'm trying to step up slowly how complicated things are. Before, things were attached by a string, but they were moving in the same direction. Here I've got one block slung over a pulley to another block, and they're moving in different directions now. So it's kind of the same, but we're going to find out it's a little bit more complicated. Here, let's see if I can show this on the video. I don't really want to change the angle of the camera, but maybe you guys can see it at home. Here's an Atwood machine. Atwood machine means you can't see. There's a pulley up here. The pulley's very light, hardly has any friction in it. I tried to make it as frictionless as possible. And equal masses on it. So of course, if I sling them over, the string's so light. If the string were heavy, then this one would start going down because it has more string hanging down. But the string's so light, it doesn't really try to go one way or the other if the masses are the same. But if I increase the mass a little on one of them, I'm just going to put a little clip on here to add a little mass to it, then it starts accelerating downward, right? And you can tell it's, tends to fall off of that when it hits the bottom. You can tell it's accelerating, right? If I release it from rest, it's going to go faster and faster as time goes on. So it starts accelerating. And so one of the goals we might find out here is, what is the acceleration? So here's my sort of equivalent textbook problem. 1 kilogram and 1.2 kilograms masses are attached via a light string. So we're assuming the string's essentially massless over a massless frictionless pulley. So we need to talk a little bit about pulleys. Again, the goal of this chapter is not just to learn F equals ma solving problems, but also a little bit about different kinds of forces. We got to know how to deal with pulleys and what kind of assumptions we're making here. So here's our, what's called the Atwood machine, very simple kind of machine. And we're going to assume, at least for right now, we're going to actually change this later in the course. So this won't be true forever, but we're going to assume that this wheel essentially has no mass. It's really light compared to the masses that it's connected to via the string. And we're also going to assume that it spins without friction. In other words, you could imagine a wheel that really had a lot of grinding on the axle, right? We're going to assume this one is very well oiled, or it's got ball bearings in it, and there's essentially no friction, and it has almost no mass. I mean, so an example of a pulley that would have a lot of mass is if you went down to the gym and took one of those huge barbells and put it on, you know, the rod in between, and then you have to really heave it to get it going. We're not talking about that. We're talking about a pulley that you can move it almost without any effort, okay? And so one of the results of that is this. If this assumption is true, it's massless and frictionless at the axis. The string tension is going to be equal on both sides of the pulley. And that's because, imagine if it weren't equal. In other words, imagine that whatever I'm doing, if I'm just holding it or I'm letting this thing go and it's accelerating, and imagine we had a big tension over here and a little tension over here on this side. Well, they can try to balance out the tension by having the pulley rotate, like putting more string on the side with the higher tension. That's going to decrease the tension on the side it rotates toward, and increase the tension on the other side if it rotates over. Now, if we're assuming it's massless and frictionless, this pulley has zero hesitation about rotating, right? There's no inertia to it. There's no friction involved in rotating. As soon as there's any imbalance, it just immediately corrects it until they balance out, and it doesn't tend to want to rotate one way or the other. So if they ever get imbalanced, so the right-hand side has a greater tension than the other side, they immediately balance each other out. So if you see the words massless, frictionless pulley, and even if you don't see them at this point in the course, like in a homework problem, they might not state it very carefully. You can assume for right now that the tension is the same on both sides of the pulley. So there's only one tension in this particular problem. Okay, let's go now back to this problem. So we've got these two things connected. With what magnitude does the system accelerate? Well, what do you mean, the acceleration? Well, what I mean is, of course, everybody knows the 1.2 is going to go down, the 1 is going to go up. But again, as fast as the 1.2 is going down, the 1 is going up at the same rate if we assume it's attached by non-elastic string. They're not moving as a unit anymore, but they're going to be moving at the same speed. So the magnitude of their acceleration is the same in this case. So let's find that magnitude of acceleration. And then, of course, because we've been doing kinematics, let's do a little kinematics problem at the end. How long in time does it take the 1.2 kilogram block to fall 0.8 meters if it's released from rest? Okay, and it turns out it doesn't matter where you release it from rest, the acceleration is the same. So I can release it from rest like this, or way down like this. The acceleration is the same once I let go of it. So it doesn't really matter where it was there. Okay, maybe it's best to do this one on the board too, just to make it slow enough for everyone to see. So let's move this camera back here. Let's get a fresh board in the way. That didn't work out so well for me, did it? Is that good? Yeah. Okay, so let's draw, again, my picture. I'm just going to draw a little cartoon of it. Ooh, that's not a good pen. If you really wanted to be artful, you could say, oh, there's something connecting it up to there. But in any case, we know how pulley works. Here's my 1 on this side and my 1.2 on this side. There's some tension, but we were just told it's the same on both sides if it's a massless, frictionless pulley. Here's how we're going to approach it. What I'm going to do is draw a separate free body diagram for this mass and this mass. And I'm going to choose what I call a consistent axis direction for both those objects, which is to say, for my first free body diagram, which I'll draw right below here, if I choose plus y to be up for this one, when this one goes up, this one's going to go down. So I have to choose plus y to be down in that one's free body diagram. Or I promise you, you're going to get horribly confused and you'll mess up a minus sign in the problem, which will make everything not work out right. And we'll see why that is when we get to it, okay? But for right now, for each free body diagram, you're free to choose any axis you want. So let's just choose it the way I'm suggesting. Separate free body diagrams, separate F equals ma. So we've got a 1. What forces are acting on that 1 kilogram? Just call it out.
Gravity and tension.
Gravity, 1 times 9.8. What else?
Tension.
Yeah, we normally don't call something a normal force unless it's sitting on a surface. So in this case, we would call it a tension force. I already gave it a name, so let's just say whatever the strength T is, that tension in the string, that force is pulling up on the 1. That's the direction it's connected, and it pulls toward the string direction always. And we are going to take plus y here. We're free to choose either direction here, but once we choose, we're constrained over here. The 1.2, it's got weight, 1.2 times 9.8, right? And it also has T going up, but we already decided, you're going to trust me on this for right now, that we are going to take plus, I'll tell you why in just a second, plus y going down for that one. And for each of these, let's write F net y equals may, right? They're both objects, so we can apply Newton's second law to it in each case. So see if I can squeeze it down here. The sum of the force y components equals may. Let's see. In terms of y components, you stop me if you're, I'm going to start to go a little bit faster on this stuff. The T comes in with a plus sign and the weight comes in with a minus sign in my chosen y coordinate system, right? T minus, I'm just going to write this as 9.8 in SI units. That's equal to the mass in the free body diagram, that's 1 here, times AY. Well, I'm not done yet. I wanted AY, but I don't know T yet. So let's hold on to this. I'm going to put a half a box underneath it. And we'll go over to this one and do the same thing. In this one, the weight comes in with a plus sign, right? And the T comes in with a minus sign in terms of y components, because I chose plus y is down. So here we get 1.2 times 9.8 minus T is equal to M. So this is, again, sum of the force y components equals may. The M is the mass in the free body diagram that I'm concerned with. And here is where I'm taking advantage of those consistent coordinate systems. I'm using exactly the same symbol here, AY and AY. If I've chosen them the way that I have, where one is going up and the other one's going down, if this one's accelerating up, it would have a positive y component, and this one would be accelerating down at the same rate, and it would also be positive. So they'll be exactly the same number, and therefore I'm justified in using the exact same symbol. If they differed at all, I couldn't use the same symbol. It should be something different, and then we'd have 3 unknowns here. Similarly, if this one goes down, AY would be negative for this one. Then this one would be going up, and AY would be negative for it. So choosing that consistent coordinate system allows me to use exactly the same symbol there. So now we're down to your old friend from high school math, 2 equations and 2 unknowns, and they're not too bad here, right? They're linear equations. So what do we want to solve for here? Let's remind ourselves, because maybe for some of you, it's been a while since you did 2 equations and 2 unknowns. The most basic technique is substitution. That's where you solve for one variable and substitute into the other equation. What do we want to know here? T or AY? AY. Should I solve for AY then? Experts in substitution? No. You always solve for the one that you don't want, because you're going to substitute in terms of the other variable. So let's see how that happens. I've got kind of a mess here because I ran out of room. So this equation is going to go back up here. Solving for T. T equals AY plus 9.8. I just added the 9.8 onto the other side. Okay. I'm going to take that expression for T, the entire expression for T, and substitute it in right there. So the whole thing needs a minus sign in front of it. Okay, so this one then becomes 1.2 times 9.8 minus all of this stuff AY plus 9.8. All of that is T, so I got to put it in parentheses because the minus sign should be in front of the whole thing. And that equals 1.2, sorry, AY. Okay, now I'm down to one variable. What do I do next? I want to solve for AY equals. Or what's the general principle I'm going to do? What am I going to try to do next? This is like our X, and I've got an X over here too. I've got X in two locations, yes. Yeah, put all the X stuff on one side and all the non-X stuff on the other. So I'm going to have a 1.2 AY. I've got a minus AY over here, right? This is really minus AY minus 9.8. So I have a minus AY over here. I can add AY to both sides and it would disappear over here. That's going to give me a 2.2 AY on the right-hand side. If you need to write an intermediate step, no shame in that. And so here I've got 1.2 times 9.8 minus 1 times 9.8. Doesn't that leave me 0.2 times 9.8? You need to write that intermediate step, that's fine. And now I just divide out the 2.2. And according to my solutions, AY is 0.891 meters per second squared. AY equals 0.891 meters per second squared. So not very close to free fall. Free fall is close to 10, right? 9.8. This is almost a tenth of that. Kind of like this, right? This is not falling close to free fall. This is something much less than 9.8 acceleration. All right, and then, you know, I don't know if it's worth doing. Let's just ask, because we got to keep reminding ourselves about kinematics. Which kinematics equation would I go to answer how long does it take the 1.2 kilogram block to fall 0.8 meters? Yeah, and I can't remember which way I wrote them down. Is the second one the 1/2 AT squared one? Yeah, X in terms of T, because we're given a T and we want an X. How far does it fall, right? So I'm going to, you know, to answer the next part, X final is X initial plus Vx initial times T plus 1/2 AX T squared. X final is what I'm after. I'm just going to call, or we could do Y. I guess I used Y's over here, but I'm just not going to change it. Imagine these are Y's. So what I'm just going to imagine wherever we release it from rest, I'm going to call that Y initial equals 0. So it's Y final that we're after. Y initial is 0. Vy initial is 0 because we're told we're releasing it from rest. You always got to read the details in the paragraph. 1/2. Oh, AX is 0 because, no, it's 9.8 because it's going vertically, right? No, that would be if it's in free fall. Here it's attached to a string and some other thing. So it's not 9.8, it's our 0.891. So the magnitude of the acceleration. So here we're talking about, is this the 1.2 that we're talking about here? Yes, so it's falling, it's going in the plus Y direction. So it's plus 0.891, right? Its acceleration is positive. And the time was, oh, I'm sorry. We're not solving for Y. We want it to fall 0.8 meters, and we want to find the amount of time that that takes. So T is what we're solving for. I didn't understand. So we multiply by 2, divide by 0.81, and then take the square root, and that'll give us our time. I got 1.34 seconds. Questions on that one? Yes. I got the 0.2 by, you know, I put the AY on this side, and that gave me 1.2 AY plus an additional AY. And then we were left with just numbers on this side. I had 1.2 9.8s minus 1 9.8. If you take 1.2 of something and you subtract off 1 of it, you're left with 0.2 of it. That's how I was thinking about it. All right, good. We're doing lots. Whoa, time is flying right now. The clock has gone crazy, but it's 1/4 till. Good, that's good timing for us. So we're going to talk about the last subject. We've been doing all sorts of forces and stuff, but we're really to the end of what we're going to talk about for a while in terms of types of forces. Let's share the screen again. Make sure there's nothing I missed here. Solving that problem. Oh, we got a voting question in here. I threw this in here because it has to do with pulleys. Here is, oh, this is more complicated. I've got a ramp with a 3 kilogram mass sliding on it. We're told the ramp is frictionless here. So no friction there. Trust me, you don't have to do any free body diagrams. You can do this all in your head. 3 kilogram mass slides on a frictionless plane after being released from rest. So I'm holding the 3 kilogram. Suddenly I release it from rest. How is the tension after it's released from rest? It's going to start accelerating down, right? The lower block's going to fall. The 3 kilograms is going to slide down the plane. Hopefully you have that intuition. While that's happening, how is the tension in the string compared to the weight of this 1 kilogram mass on the bottom? Larger, equal to, smaller? Okay, let's see a vote. I'm not sure everyone's ready to go. You don't really need any calculation you do, you can do in your head. There's no diagrams that are needed or anything for this. If you have a vote, some conviction, hold it up. Let me just see if there's any agreement in the class. Okay, I see A's, B's, and C's, and a no clear winner here. So that's usually we need to have a little discussion or detailed discussion here. Anybody really think they understand how to think about it? Have a strong conviction of one of the answers? Or want to explain what they were thinking? Okay, someone in the class just said, I don't think it could be C because. Okay, if the tension were smaller than the weight, it wouldn't be able to keep it in the air. So that means it would go into free fall or something like that. Okay, someone on Zoom was going to jump in there.
Yeah, I was gonna say, like, we know the force downward, so it'd be like T minus the downward force equals like M times A. And then when you solve for T, like you're gonna add the downward tension. Yeah, so then it's gonna be greater than the mass, the weight of the 1 kilogram mass.
Okay, so you're saying A, I think, right?
Right, yeah.
Larger than the weight of the 1 kilogram mass. Anybody else want to weigh in? Oh, I gave it away. Clicked on it. You see, I sometimes highlight these in red. Maybe some of you didn't notice. The correct answer is actually C. This is a really tricky question for most people, most semesters, but you know everything you need to know about this. Let's just take B. Suppose they were equal, right? Suppose this tension exactly balanced out the weight force on the 1 kilogram. What do we know about what the 1 kilogram would be doing or not doing? Yes. Well, it technically could be moving, but it wouldn't be
pulling the same.
accelerating because the net force, if this upward force is exactly equal to its weight downward force, the net force along that direction is 0. And that means that component of the acceleration is 0. There's no horizontal or other forces on it, right? The only two forces are the tension and its weight. So it wouldn't be accelerating. Now, I'm taking that everybody knows if I let this thing go, it's going to start moving. And therefore, there is some acceleration. The 1 kilogram mass is accelerating down, right? It starts to rest, and it goes faster and faster and faster. And this one's going to go faster and faster down the plane. All right. Anybody want to choose between A and C now? Who's got to win out of those two forces if it's going to accelerate downward? Well, my answer is up there. It's smaller than. The tension has to be smaller. Who wants to explain why the tension has to be smaller than the weight? What if the tension were larger than the weight? Yeah.
Well, I mean, for the tension to be larger, the mass of the, I guess you'd have to switch them. I guess it never could be, because it's a, they don't always have a balance of the mass, but like the tension of 1 kilogram, it will only be 1.1.8.
Yes.
It won't be harder than that.
Right.
The 3 kilogram block will not push the string.
Yes. So there's no doubt that it can't push the string. And in my argument, I'm trying to construct here, I'm only really looking at this bottom part and taking the knowledge that I know the 1 kilogram is going to start accelerating downward. Yeah.
If the tension was larger than the box, the 1 kilogram box would go down.
Yeah, it wouldn't go down. In fact, it would go up. It would start rising up, right? And everybody knows that's not going to happen. If the tension, notice Newton's second law, sum of the force x components or y components equals may. It says, whichever way the net force points, that's the way it's going to accelerate. If the tension is bigger than the downward weight force, the tension wins and it's going to accelerate upwards. And we know it's not going to accelerate upwards. It's going to start falling downwards when I release it to rest, right? Even if I push it up and release it, it still is going to start slowing down in the upwards direction, which is a downwards acceleration. So the weight's got to be bigger than the tension force in order for it to have a net force in the downward direction and therefore an acceleration in the downward direction. The reason I'm warning you about this is because, there will be a lot of problems where things aren't accelerating. We've already seen plenty of them. And if this were not accelerating, in other words, if I were just holding on to the 3 kilograms and everything was sitting still, the tension would balance out the 3 kilograms weight. And you'll see a lot of times students who aren't used to thinking about this will just say, oh yeah, the two balance out. Everything balances out, right? Just like if I have a mass on a block, I could say, hey, this isn't accelerating, and therefore the weight force and the normal force balance out. But if I'm letting it accelerate downward in that moment, the weight force has to not balance out the normal force. If the force is balanced, there's no acceleration. It is accelerating when I let it go down. So the weight force has got to be winning out over the normal force, and that means the normal force got smaller because the weight force doesn't have a choice. We're near Earth here. Your weight is what it is, but the normal force can adjust and be different values. So the lesson there was just don't assume that forces balance out. That's not the total confusion here, but just remember, the net force is always the direction of the acceleration. We'll see that again later on. Any more questions on that one? Got to keep my phone out because the clock's not working. Okay, let's go on here and talk about friction, our last topic here. We're going to talk about two kinds of friction force. The first one is called the kinetic friction force that you read about. That's where one surface is sliding and grinding against another surface, like this block on the table that I'm pushing across here. I would say that as I push the block in that direction, there's a kinetic friction force that the table is exerting on the block in the opposite direction from which it's moving, right? So if I push the block to the right, the table is exerting a kinetic friction force on the block. Well, it's to my right, to your left, right? It's exerting a kinetic friction force in that direction. Kinetic means moving, and the moving part here doesn't concern the fact that anything's moving. It means that the object is moving relative to the surface it's on, So it's grinding against it, and that's going to be important because it can be confusing. Okay, so here is a free body diagram shown, oh, a part of a free body diagram. There's an applied force. I'm imagining I'm pulling this block at maybe constant speed, right? So I've shown one of the forces on the top, but let's draw a full free body diagram. What forces are on it? There's a normal force up from the table. It's a horizontal table. There's a weight force. We're familiar with that. I'm pulling it to the right. It's moving at constant speed, so there's got to be a kinetic friction force going to the left. If there weren't, it would be accelerating in that direction. Otherwise, there'd be a net horizontal force in that direction if there weren't a friction force. So if I'm pulling it at constant speed and I'm applying any force at all, there's got to be a kinetic friction force of equal magnitude in the opposite direction to keep it going at constant speed. There would also be a kinetic friction force if I were accelerating or letting it slow down. Anytime there's grinding, this is just one example. Okay, some things you learned about the kinetic friction force that it depends on. It depends on, of course, the materials at the sliding interface. It depends on the fact that this is wood and this is a certain kind of plastic that has a certain roughness. If I change this wood and put a rubber coating on it, the friction force is suddenly going to get bigger. And if I coat it in Teflon, the friction is going to get smaller, right? So it depends on both of the surfaces that are grinding against each other. It also depends on the normal force at the sliding surface. In other words, when I'm pulling this along, I've got sort of a moderate normal force that I'm pulling along with here. If I all of a sudden put this kilogram mass on there, right, you can imagine all of a sudden the force between the table and the block has gotten a lot bigger. And you can also imagine that it's a lot harder for me to pull this, which means there's got to be a bigger friction force going back, pulling it against my motion. Okay, so both of those are, I think, are pretty clear. What maybe isn't so obvious is that it is roughly, this is not a fundamental law of physics, but just a rough model that's sort of true. It's roughly independent of the shape or area of the sliding interface. In other words, the claim is this. Here's a big area on the bottom of this, certain friction force. And if I turn this on its side and I pull it at constant speed, the claim is, according to this model we're constructing here, it's about the same friction, even though it might seem like bigger area, bigger friction. But what matters is the normal force. As long as the normal force is the same, and the normal force is the same, it has to be exactly big enough to keep this from accelerating against the weight of the block. And the weight of the block isn't changing when I rotate it like that. So roughly, it doesn't depend on how big the surface area is that's contacting the surface that it's sliding on. It's also roughly independent of the speed of sliding. Again, this is not something that is extremely true. It's just sort of, it doesn't depend very strongly on it at all compared to these other two things. So if I pull it at 0.5 meter per second or 0.75 meter per second or 1 meter per second, roughly the same friction force. It's not exactly true. Here's a friction law that captures that. So we're going to call, because this is kinetic friction, the kinetic part means the two surfaces are grinding relative to each other, right? One is sliding on the other one. That's the kinetic. You can calculate the magnitude of the kinetic friction force by, it's proportional to the normal force. So if I double the normal force, if I take a block and then compare a 1 kilogram block and compare it to a 2 kilogram block, we're going to see a rough doubling of the friction force size, right? Heavier things have more friction holding them back. That hopefully that makes sense. So it's proportional to the normal force, and the constant of proportionality is called mu, lowercase Greek mu with a subscript k. The k is for kinetic, and this is called the coefficient of kinetic friction. And that is the part that depends on the materials at the sliding surface. So different surfaces on different surfaces will have different mu k values. Larger mu k's mean more friction, everything else being held the same. Okay, so it's a pretty simple law. Let's skip that one. This is essentially what I was just talking about. You're pushing a crate and you slide it on its, you put it on its side, so you have the surface area contacting the floor. The friction force, according to this law, is going to be about the same. Okay, there's nothing in this law that mentions the surface area there. It's only the normal force, and this depends on the material. So nothing about surface area nothing about speed. Okay, so that's kinetic friction force. That was one kind of friction force that you talked about. Static friction force is also a force of one surface on another, but in this case, the two surfaces are not grinding against each other. It would be like this. Here is a, try to aim this so people at home can see. Here's a kilogram mass right here. I'm going to put it on the table. And I'm going to apply a feather light force on this side. And of course, it doesn't move, right? Why doesn't it move? Well, what's a free body diagram for? Well, of course, it's got a normal force. It's got a weight force. It's got my force going in that direction, but it's not accelerating. So there's got to be an equal and opposite force in that direction. And it's because the table is holding it back. It doesn't want to let it go, right? There's some sort of, at the molecular scale, there's some chemical bonding that's taken place. And you got to break those bonds to get it free. And we haven't pushed hard enough to break the bonds. Okay, I'm pushing a little harder now. Nothing happened. You can't see because it's not moving, but trust me, I'm pushing harder. I'm pushing harder. Nothing's happening. I'm pushing a little harder. It starts moving, right? At some point, it breaks free. If you got a really heavy box, you push on it harder, push on it harder. Suddenly, it breaks free. You know, we all have done something like that before. So static friction, unlike kinetic friction, kind of has two kinds of laws, and you may only remember one of them from the reading. Okay, here's my free body diagram looking very similar, except that this is not moving in this case. It's hard to tell, but it looks kind of the same. I'm pushing to the side, but it's not budging. Here's the free body diagram. There's got to be a friction force balancing out my applied force because the acceleration is 0. Otherwise, there would be an acceleration along the horizontal direction. That force we call the static friction force. Static means the two surfaces are not moving relative to each other. They're not sliding or anything like that. So we use a S for static right there, okay? Here's me pushing with not enough force to move it, a puny force. When I push with a puny force, the friction force back is puny. They got to exactly balance out because it's not accelerating, right? There's the horizontally speaking, they've got to balance. If I push with a bigger force, it pushes back with a bigger force because it's not accelerating. If I put, so as long as I don't push too hard so that it starts breaking free, one way to describe the static friction force, as long as you don't push too hard to make it break free, you could say the static force always exactly balances out the applied force parallel to the surface. So I wrote that as F parallel applied. The components of the force that you're applying parallel to the surface. Static friction's got to balance it out because there's nothing else pushing along that direction. But if I push a little bit harder, I might be pushing it just the amount so that if I push any harder, it's going to break free and start moving. We would call that the maximum static friction force. So we'll denote that by Fs, max. For every set of surfaces and normal force that are interacting like this, there's some breaking point. And of course, it depends on the materials, right? If you have rubber on rubber, the breaking point is going to be larger. If you have Teflon on Teflon, it's going to slide very quickly. But every surface is going to have some breaking force, some maximum force that it can exert back. And if you push any harder than that, I'm imagining we're just about to go harder than that right here. If you push any harder than that, it's going to start breaking free. And then we won't be talking about static friction anymore. Then it would be kinetic friction because the surfaces would be grinding against each other, right? So again, what does this maximum force? This is just, this force, Fs max, just tells us about the breaking point. When is it just going to barely give way and start sliding? That maximum force that friction can exert depends on the materials, of course, rubber on rubber or Teflon on Teflon or wood on Teflon or whatever, and the normal force at the sliding surface. You probably have the intuition that if I take this block and I put a 1 kilogram block on it, it's going to be harder to get it to budge. I'm going to have to pull harder. Or even if I just push down on the top of it and then try to pull it, I'm going to have to pull harder before it budges. So we're talking about that in this maximum part. We're talking about when it budges. Again, it doesn't depend on the shape or area of the sliding interface, very roughly. That's not exactly true, but just sort of a rough law. And we don't need to talk about the speed of the sliding because it's not sliding here. It's just stuck to the surface. So there is no speed to talk about here. Okay. Now the tricky part is this law that tells us about the breaking point, the maximum static friction force that can be exerted, looks almost exactly like the one for the kinetic friction force. There's a coefficient of static friction, whoops, we call that mu s, mu with a subscript s, and that depends on the materials at the sliding interface or at the stuck interface. And the normal force is just how hard the surfaces are pushing against each other. But notice the interpretation is very different. This tells me about a breaking point. It has nothing to do with if I'm pushing on a box and it's not about to break free, I should not be using this law down here. I should be using this one up here. Because if it's not about to break free, it's just balancing out what I'm doing. It's only if I know it's just about to give way that I use the, oh, did I misread my phone? Because that, no, it's 4:05. Okay. Have a good weekend. I noticed some strange looks and I was thinking, well, I just checked my phone. If you have questions, feel free to ask. I think